Okay, we're going to look at double angle identities and where they come from. And as far as most pre-calc classes go, we're going to be concerned with two of them, sine of 2x and cosine of 2x. So for sine of 2x, the best way to derive this is just think of 2x is simply the sum of x and x, and then apply the formula for the sine of a sum of two angles on these two angles. I always call this one the first one and this one the second one. Obviously, in this case, they're both the same, but that kind of helps me remember the formula for the sine of a sum of two angles. It's the sine of the first angle times the cosine of the second angle plus the sine of the second angle times the cosine of the first angle. If you realize that these are like terms, we could combine those two together and just say we have 2 sine x cosine of x. And there is our go-to formula for whenever we see sine of 2x, we can use its equivalent, which is 2 sine x cosine of x, which is convenient because we have a single angle that we can reference as opposed to a double angle. For cosine of 2x, we're going to do the same idea. We're going to apply cosine of x plus x, remembering the cosine of a sum is cosine of the first angle, cosine of the second angle, minus sine of the first angle, sine of the second angle. And of course that can be rewritten as cosine squared of an angle of x minus sine squared of x. So as far as cosine of 2x goes, the most common substitution would be this, that you can replace it with cosine squared minus sine squared, not to be confused with cosine squared plus sine squared, which is of course equal to 1. However, I would say this one kind of comes in three flavors because one thing we could do is take that cosine right there and replace it with its equal, that cosine squared, which is 1 minus sine squared of x, and then subtract the sine squared of x, and we have a second version of cosine of 2x, which is 1 minus 2 sine squared. This one can come in handy if you're working in an equation or an identity where you need to work in sine ratios as opposed to cosines. And then lastly, we could have taken this original derivation that we got, which was cosine squared of x minus sine squared of x, and rather than replacing the cosines with sines, we could replace this sine squared with 1 minus cosine squared. So I'm going to put 1 minus cosine squared in there for that sine, and realize now that we have cosine squared minus the quantity 1 minus cosine squared. Distributing that negative to the 1 and to the negative cosine squared is going to give us cosine squared minus 1 plus cosine squared, which is 2 cosine squareds minus 1. So there's our third flavor, if you will, of cosine of 2x. So we have the basic one, cosine squared minus sine squared. We have 1 minus 2 sine squared and 2 cosine squared minus 1. So all three of those are useful. You just kind of pick your battle as far as which one you want to use at which time. Okay, not to be forgotten, we have the tangent of 2x also, which can be dealt with by just using the sine of 2x over the cosine of 2x. But for its own sake, working in tangents, we can use the tangent of a sum, which is tangent of the first plus tangent of the second angle over 1 minus the product of the tangent of the first angle and the tangent of the second angle. So simplifying that, the numerator is simply 2 tangent of x, and the denominator is 1 minus tangent times tangent, which is tangent squared. So if we ever need tangent of 2x, we can go there. But again, sometimes it's just as effective to just think sine of 2x over cosine of 2x. So for this particular problem, we are told that we know about some angle theta that has a sine of 7/25, and they're asking us to complete this collection of information for all these other ratios for twice that much of an angle. So what we know is that the sine of our angle is 7/25, so it says draw a triangle corresponding to that ratio. So we have an angle theta whose opposite side is 7 and whose hypotenuse is 25. Now, if you think of this unknown side length there as x, go do Pythagorean theorem and you say x squared plus 7 squared equals 25 squared. You're going to find out that x is 24. That 7, 24, 25 is a good Pythag triple to recognize. Comes in handy. But anyway, now that we know that this side is 24, we know every possible trig ratio we could about theta as far as its sine, its cosine, its tangent, and their reciprocals, cosecant, secant, and cotangent. So for maybe reference, we can make a quick list of them. We know the cosine of that angle would be 24 25ths, and the tangent of that angle would be the opposite, which is 7, over the adjacent, which is 24. So if we need, as they're asking us in this first problem, the cosine of 2 theta, we could come over to our little chart that we developed on the last slide with information about cosine of 2 theta. We could use any one of these three. I'm just going to use the first one, cosine squared minus sine squared, because that's kind of like the go-to that we use when we need one. So this is the cosine squared of our angle minus the sine squared of our angle. But we know both the cosine and the sine. The cosine is 24 25ths, so it's 24 25ths squared minus the sine, which is 7 25ths squared. And, we have some numbers here, so, calculator would come in handy. I do know that 25 squared is 625, so that's going to be our denominator in both. And 24 squared, which is 576 minus 7 squared, which is 49. And whatever, 576 minus 49 is, let's say if it was 576 minus 50, it would be 526. So it's going to be 527. So that answer is 527 over 625. For the sine of 2 theta, we're just going to use our 2 sine theta cosine theta, which is 2 times the sine of theta, which is 7 25ths, times the cosine of theta, which is 24 25ths. Again, my denominator is going to be 625. And if you take 2 times 7, which is 14, and then multiply it by 24, I think you're going to get 336. So 336 625ths. And lastly, for the tangent of 2 theta, we can use our tangent of 2 theta formula, which is 2 tan theta over 1 minus tangent theta squared. That's the tangent of 2 theta. So we have twice as much as the tangent of theta, which is twice as much as 7 24ths, over 1 minus the tangent squared, which is 7 24 squared, which is 49 576. So we have 14 24ths over 1 minus 49 576. Simplify that complex fraction, you get a common denom, and you're going to wind up getting 336 over 527. Now, the shortcut to that is to realize that we could have just done tangent of 2 theta as the sine of 2 theta, which we found out in part B as 336 over 625. Take that and put it over the cosine of 2 theta, which we found out to be, the cosine was 527 over 625. This one was the cosine, this one was the sine. And of course, to simplify that, you get 336 over 625 multiplied by 625 over 527. So we're taking this numerator, which is there, and multiplying it by the denominator reciprocated, and you get the 625s are going to cancel out, and of course you get 336 over 527. Kind of nice to see that it gets the same answer either way. So really no need to go do the cosecant of 2 theta, because all you have to do is reciprocate the sine, which was that 336 over 625, so that one's just going to be 625 over 336. The secant, you're reciprocating the cosine, so this one, which is going to be 625 over 527. And then lastly, the cotangent, you just have to reciprocate the tangent, which is right there, so that's going to be 527 over 336. So nothing too crazy there, pretty typical pre-calc questions. Okay, for this next set of problems, we've got equations. We're trying to solve for a value of x or values of x that are going to make this true. And I have a few suggestions for when you're trying to solve trig equations. One is to try to keep things simple. Try to get things in terms of sines and cosines. Obviously, this one's already in terms of sines. Next is kind of a big picture thing. Generally, most of these are solved by setting them equal to 0 and factoring if possible. But lastly, and perhaps most importantly for this particular section on double angles, is you need to make sure that the arguments that you're working on here, the sine of this x and this one, which has the sine of 2x, those arguments all have to be the same. You don't want to be dealing with equations with terms that are being added and subtracted that have two different arguments there. So I always say, where do we want to focus on this thing? And I think we want to focus on the sine of this 2x so that we can use this conversion factor up here, that we can turn that into 2 sine x cosine x. That's our first step. So we rewrite this as 2 sine x cosine x minus the sine of x is equal to 0. And now we have a nice setup in that, I said the fundamental strategy is one of the things to do is set it equal to 0 and factor. Well, we now have a common factor of sine of x in both terms. So you can take a sine of x out and be left with 2 cosine of x minus 1 equal to 0. And then once an equation's factored, you set each factor equal to 0. So either sine of x equals 0 or 2 cosine of x minus 1 equals 0. Sine of x equals 0, that's going to happen in one trip around the circle, which is what we're looking at here from 0 to 2 pi. The sine will be 0 at 0 and pi. And 2 cosine x minus 1 equals 0. That's going to be the same as saying the cosine of x is equal to 1/2. Add the 1, divide by 2. Cosine is 1/2 at pi over 3 and 5 pi over 3. So knowing your circle is clutch to be able to finish these problems out and know where those ratios occur. So this next one's very similar. Again, we want to set these things equal to 0, so I'm going to say the sine of 2x minus the cosine of x is equal to 0. And then we want to turn that sine of 2x into 2 sine x cosine of x minus the cosine of x equals 0. And this is almost identical to the last one, only instead of having a common factor of sine, you've got a common factor of cosine. So you're going to factor that cosine out and proceed like we did in the last example. Probably take it from there. Similarly, this next one, again, we're going to do the sine of 2x cosine of x. Then we're going to subtract that sine of x over, and leaving 0 on this side. Turn the sine of 2x into 2 sine x cosine x, which is being multiplied by the cosine of x, minus the sine of x, which is equal to 0. And we do have a common factor of sine again. We're going to get a slightly different type of answer here, though. When we take that sine of x out, we're left with 2 cosine squared of x, because we have two factors of cosine here and here, so multiply them together to get cosine squared. Minus 1 is equal to 0. So setting the sine of x equal to 0, we're going to get our 0 and pi again. But this guy, 2 cosine squared of x minus 1 equals 0, is like saying 2 cosine squared of x equals 1, is like saying cosine squared of x is equal to 1/2. Now we have to take square roots of both sides, and remembering that we can have a positive and negative root, we get cosine of x equals plus or minus the square root of 1/2, which is plus or minus the square root of 1 over the square root of 2, which is plus or minus 1 over root 2. And when you rationalize that denominator, you get plus or minus root 2 over 2. So you should recognize root 2 over 2 as the sine and the cosine at pi over 4, but because we're talking about positive root 2 and negative root, positive root 2 over 2 and negative root 2 over 2, what's going to happen is we're going to get that cosine to be positive root 2 over 2 over here and negative root 2 over 2 for those angles there. So it's all of the pi over 4s. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And then lastly, this equation is a little bit interesting because we've got a mix of sines and cosines going on here. So I'm going to start by moving everything over to one side. So sine squared minus 2 minus the cosine of 2x is equal to 0. And I referenced this earlier when we were talking about coming up with these formulas for cosine of 2x, in that there's 3 different flavors, as I called them. For this particular example, because we've got a sine squared of a regular x and a constant, it would be really nice if we could replace this thing only with sine values, or a sine ratio, as opposed to mixing in sines and cosines together. So if we use this third option of 1 minus 2 sine squared, I think that's going to benefit us. So I'm going to do just that and take sine squared of x minus 2 minus the cosine of 2x, which is getting replaced with 1 minus 2 sine squared of x equal to 0. So I just replaced that guy with its equivalent. I'm going to distribute the negative, and we're going to get sine squared of x minus 2 minus 1 plus 2 sine squared of x is equal to 0. And I guess that gives us what? Sine squared plus 2 sine squared is 3 sine squareds of x minus a 3 is equal to 0. And you can either factor out the 3 or divide through by 3, but that's going to get you sine squared of x minus 1 equals 0, which means the sine squared of x equals 1. Taking square roots of both sides with a plus or minus means sine of x could be plus or minus 1, and that happens at either pi over 2 or 3 pi over 2. And there's your answers for that guy. So good collection of examples there with lots of different problem types using the double angle identities. Okay, for this last one of these equations, we have a tangent involved, tangent of 2x minus tangent of x. And so it's not terribly different than that one that we did on the last slide. I think we had a sine of 2x minus a sine of x. In any case, we could treat this like sine of 2x over cosine of 2x, and this is sine of x over cosine of x there. That's going to get a little messy though, so I think we would just want to break down and use the tangent of 2x identity, make that substitution. So instead of this tangent of 2x, we are going to write 2 tangent of x over 1 minus tangent squared of x, and then we're going to subtract the tangent of x. And we're saying that that's got to be equal to 0. Now, the big strategy here is set it equal to 0, which it already is, and factor. And we do have a common factor of tangent of x in both of these. So if we take that factor out, we get tangent of x. And when we pull this tangent of x out of this factor, we're left with 2 over 1 minus tangent squared. And when we pull the tangent out of that, we're left with a negative 1, and that's equal to 0. So that we are now in factored form, and so we get either this factor or this factor equals 0. Maybe I'll do this one in red. So the tangent of x would be equal to 0. Basically, tangent flies along with sine, in that whenever the sine of a function is the sine of an angle is 0, the tangent is 0. So that's going to happen when x is 0 or pi. This factor is a little bit more complicated. We've got 2 over 1 minus tangent squared of x minus 1 has to equal 0. So the algebra on this, just kind of follow along. I think what I want to do is put this 1 over to the other side, and we get 2 over 1 minus tangent squared is equal to 1. And kind of think of that 1 on the right side like 1 over 1, and we can do a little cross multiplying. So 2 times 1 is 2 is equal to... So in other words, this guy times that guy is 2, and 1 minus tangent squared times 1 equals 1 minus tangent squared. So we're going to get 1 minus tangent squared over here. And we could subtract 1 from both sides, and we get 1 equals negative tangent squared, which if we divide both sides by negative 1, we get negative 1 equals the tangent squared of x. And we can just stop right now because a squared quantity will never be negative. So there's no solution that's going to come from this portion of the equation. So that didn't give us anything, so we're just going to stick with these two solutions that we got from tangent of x equaling 0, and we've got our solutions. Now, I'm not going to go through all of these 3, 4, and 5 here that are left, but if we get one of them, you'll kind of see the deal. Maybe I'll do this one because it's a little bit more interesting. So we've got a situation where we have an angle theta that has a cotangent of 4/3, and it's in this quadrant between pi and 3 pi over 2. So if we think about that, pi is here, and 3 pi over 2 is down here. So our angles, terminal side, must be here, like that. So we can think about that angle kind of coming around that way. And we can think it's reference angles right there. Drop a perpendicular back to the x-axis. And we know that cotangent is 4/3. So that means the adjacent over the opposite is 4/3. Tangent would be opposite over adjacent. This is adjacent over opposite. We should recognize that the hypotenuse would be 5, the radius would be 5. But those 4 and the 3, you have to recognize that we went to the left and we went down. So both of those guys deserve a negative sign. And now we have a situation where they're asking for the cotangent of 2 theta. So what we're going to do is recognize that the cotangent of 2 theta is instead of the sine over the cosine like tangent is, it's the cosine of 2 theta over the sine of 2 theta. And then, kind of like what we did on the other page, doesn't really matter which one we use. Why don't we go with cosine squared of theta minus sine squared of theta for the cotangent, for the cosine of 2 theta, and for the sine we just use 2 sine theta cosine theta. And all we really got to do is drop the numbers in for each of those things based on our diagram. So cosine squared would be -4/5 squared minus the sine squared, which is -3/5 squared, all over 2 times the sine, which is -3/5, times the cosine, which is -4/5, and we're going to get our answer. So the numerator is 16/25 minus 9/25, and the denominator is, let's see, -3 times -4 is 12, times 2 is 24 over 20. So we have 7/25 being divided by 24/20, which is 7/25 times 20/24, and 20 over 25 reduces to 4 over 5. So we've got 7 times 4, which is 28, and 5 times 24, which is 120. I guess we could have done some more reducing there. This 4 and this 24 is a 1 and a 6. So 7 over 30. And there we go. So the cotangent of twice the angle is 7/30. So you can see that these other two problems, this one and that one, would be very similar, where you just have to draw the triangle, figure out what the missing side length is, and then apply the appropriate formula. So there you go.